Okay, so today, totally review of Science 10. I teach you nothing new about the law of conservation of mechanical energy. Okay? Because you can't, it's a law, and that's really as far as it goes. Okay? Energy cannot be created, it cannot be destroyed. In the absence of non-conservative forces, the initial energy, the initial mechanical energy will equal the final mechanical energy. Okay, in Science 10, you would have written that like this. EI equals EF. Okay, an important part of the law of conservation of mechanical energy is that energy can be converted. It can't be created or destroyed, but it can be converted into other forms. When we're dealing with the law of conservation of mechanical energy, that is going to mean from some form of potential energy, either gravitational or elastic, to kinetic. Okay? If there's any heat or anything like that, those are not mechanical, that's wasted energy. Okay? That's not going to make it seem like it's conserved. Right? So we're going to be dealing with situations where one form of potential, okay, is converted into kinetic. For this unit, that's going to be gravitational potential. We'll talk about elastic when we talk about unit 4. Okay, so the good news here, you will not have to solve questions any harder than what you did in Science 10. So those roller coaster questions you did in Science 10, that's what we're doing today. Okay, exactly the same as those. Right? When we get to unit 4, all that will change is we'll substitute in elastic potential energy for gravitational. It's just a different formula, but everything else works exactly the same. Okay, instead of mgh, you'll have 1/2 kx squared. Okay, still works the same way.
It's going to be on our test on Monday?
Yes.
Yes.
Yeah. Okay, so 2 kinds of energy, okay, that contribute to mechanical energy, kinetic and potential. There's different forms of potential, okay, but it comes down to it's kinetic and potential energy. Okay, so you calculate total mechanical energy by adding together EK plus EP. We've been doing that already with our work energy theorem problems. Okay, so if there are any non-conservative forces, okay, those are ones that make it appear as though energy hasn't been conserved. Okay, that's what we were doing earlier when we did work energy theorem. Okay, the work against a non-conservative force, or whatever it is that's different, okay, is going to be the final energy minus the initial energy. In a conservation of energy problem, this minus this equals 0 because there's no work being done and all the energy is being conserved, which is why we can write it like this. EI equals EF, and when we expand it out, that's going to be EP initial plus EK initial equals EP final plus EK final. And then you manipulate, plug in the rest of the formulas, okay, manipulate again, and then you're set. Okay. okay? Just like you would have in Science 10. Okay, so on a roller coaster, obviously near the top, you will be moving very slowly, okay, and have a lot of potential energy, so low kinetic and high potential. As you accelerate down that slope, okay, obviously your potential energy decreases because you get closer to the bottom and h gets smaller, but you also speed up, so v gets bigger. All of the potential gets converted into kinetic, okay, because we're dealing with an isolated system or perfect system where no energy is lost to friction or anything else. Okay? Obviously in the real world, energy is lost to friction and other things. If you've ever stood next to a roller coaster, even take out all the screaming, it's still quite loud. Okay? Just the mechanical parts of it moving, okay, are very, very loud. There's a lot of friction. Okay? Back when we used to go to West Edmonton Mall, that was like when we did the whole amusement park thing. Okay? Next to the Mindbender, which now doesn't exist, part of the reason we don't go anymore, okay, it was super loud. When they were just running it as a test run, they would put sandbags in the seats and just run it. It's still loud, okay? Even though there's nobody on it screaming, it's still loud. There's a lot of friction there, okay? There's heat, there's sound, all of that coming off. And the whole track sways, okay? It's designed to flex, right? All of that represents energy that's not staying in the train. Right? Enough of it stays in the train, it gets going pretty fast. It goes from 0 to, I think it was 86 kilometers an hour, okay? It's like 1.5 seconds it takes to get to the bottom of that first hill. It gets fast, okay? You accelerate really, really quickly. All right, and then obviously at the bottom, minimum potential energy because your height is low, maximum kinetic energy because you're going really fast, and then any other little bumps that go along as you go along the roller coaster, okay? It's all getting converted 100%. If this was a roller coaster that could exist in reality, you'd just have to be towed to the top of the first hill and then you'd never be able to get off. Because it would just run forever. Okay? It would always convert 100% of the energy back. Okay? Obviously that's not what happens. That's why, like on the Mindbender, the first hill was really, really high, and then you go down, go through some loops, but the second hill was only about half as high as the first one, okay? And then after that, you had maybe a loop or something, but it wasn't as high as that second hill, because all the way along, you're losing energy, okay? If you build the second hill too tall, the roller coaster won't make it all the way up, which would be scary in its own right, okay? Anytime a roller coaster stops or does something it's not supposed to do, it's scary. Take it from me. We were on the Mindbender once when it did something it wasn't supposed to do. They stopped it. The top of the first hill, we were just about to go, and the brakes came on. And we're sitting there against our harnesses looking at our imminent demise. Okay? And we stayed there. It seemed like an eternity, but it was probably only about 5 minutes or so. And nobody comes on the speaker, nobody says anything, we gonna die. We all gonna die, okay? And yeah, you should have seen the kid next to me. He had pulled like a full Mel Gibson Lethal Weapon / Houdini. He was like gonna dislocate his arm and get out. Okay? He was halfway out. I'm like, where are you gonna go? Like, look around you. Are you Spider-Man? Like, you're not getting, where are you gonna go from here? Okay? Better off to stay in this thing and crash than to fall. But yeah, and then they just let it go. Nobody comes over the speaker to say anything, just all of a sudden the roller coaster starts to go. Quietest Mindbender ride ever. We were too terrified to even scream. Just thought we were all gonna die. And then they took us all off, put the sandbags on, and ran it a couple of times. We're like, I haven't ridden it since. Now no one can ride it because they took it down. But yeah, I'm not a human sandbag. Scary. Okay, everybody with me on this part? Okay. Okay, so final mechanical energy is equal to the initial mechanical energy. Okay, so that means the total mechanical energy is constant along the path between the initial and final points. Okay, so as this cart was to go down this hill and go through these loops and everything, okay, all that would happen is kinetic and potential would switch places. These two gauges would go up and down, but this gauge would stay constantly full. The total mechanical energy would never change. These two, when one goes down, okay, the other goes up, so they just keep doing this, right? They'll always add up to a full tank for the total mechanical energy. All right. Now, you all know that I'm a nerd. Okay, we've gotten past that point. Okay, I also used to coach track and field. And we went to track and field provincials in Edmonton. So this is at Foot Field in Edmonton. They have this device there. Okay, and the first time I saw it, again, remember I'm a nerd. Okay, I went and grabbed the whole team and I brought them over to the shot put area. I'm like, guys, look at this. They're like, what the hell is wrong with you? Yeah, they put the ball on it. No, but watch. Put the ball up here, and it would roll all the way down. And then right here is where the throwing circle is. Every single shot put stops right there. Not because there's something to stop it. It just rolls to a stop at exactly the same spot. As long as you place it, don't push it, just place it at the top of the ramp and let it roll down the ramp, and it would always stop. So it's not like the bowling alley where you can get your fingers caught between the bowling ball and another bowling ball, right? But they slam into each other all the time. Okay, this would stop at the very end. So a shot put could never roll off the track onto somebody's foot, okay? Squish anybody's fingers. It could never happen. They would always roll to a stop at the very end. I found out they actually had the Faculty of Engineering at U of A fabricate this. It is designed so that the work done in placing any shot put here, okay, it's potential energy here, it'll be converted to kinetic. Here's where the maximum kinetic energy will happen. They know the coefficient of friction of the track. They know that this is the distance required for the force of friction to take away all of the kinetic energy, turning it into heat and sound, so that when it gets to the end of the track, it stops. Works every single time. I know nobody appreciates it like I do, and that's okay. It's like basically the whole track team's like, give me that same look that I get every time I explain something that I think is really cool to people, and I'm like, yeah, but it's cool because it's science, and that's, yeah, anyway. So it's just a perfect example of, hey, we applied this, what we're learning, conservation of energy, work energy theorem, okay, all that stuff we're learning can be applied to a at least somewhat useful practical purpose. Okay, if the bowling alleys did this, no little kids would ever get their little fingers squished, okay, in the machine. Okay. All right. Okay, so if we had bobsled, okay, or any other Winter Olympic sport where you're taking something and going down a hill, skiing, luge, skeleton, okay, which, I mean, because luge wasn't crazy enough, right? There were people that wanted to go down head first, right? That was how skeleton was born, right? Luge wasn't crazy enough, so let's go down head first. Okay, so we put people up at the top, okay, and if we just get in the sled, we would only have potential energy at the top, and then travel all the way down, and we would still have, you can see here, that number, that 600,000 joules, is the same all the way to the bottom. Now, in the real sport, we have potential energy, but what do they also do to their sled? They push it. So they're doing some work, but the moment everybody jumps into the sled, you have a certain amount of mechanical energy. You will have that amount of mechanical energy when you get to the bottom, if it's an isolated system. Obviously, it's not. Now, here's another sadder application of this. Okay? In 2010, Vancouver hosted the Winter Olympics. During the practice runs for the skeleton, one of the athletes was killed because they got freezing rain on the track, which is normally covered in ice. Okay? But the freezing rain covered it, and it was even more slippery than usual. When the person got to the second corner, they were going way faster than the corner was built for, right? Normally the corners go way up. This corner wasn't built high enough, and they exited the track and were killed. Now, you can't redesign the track. You can't throw sand on it, okay, like you would on the road to make traction better. Okay? What was their solution? They obviously had to make it safe enough. They couldn't build the corner higher. It was too late for that. How do you make sure they don't have enough energy to leave the corner?
You don't push as far.
Close. They still pushed.
Start them lower.
Start them lower. Simple solution. No records set that time because they had a shorter track. Okay, but yeah, they had to start them lower simply because that was an oversight. Same thing that happened with a water slide, right? If they don't build the corner up high enough, right, you could fly out, right? Yeah.
There was a water slide in Kansas City. We were known for the tallest water slide in the world, and they went up, and then it was a big loop, and when they went up, a kid got decapitated by a,
By the tunnel?
yeah.
You feel like at some point the designers needed to see that, right? Like, yeah. There's also one where they built it like that and the person flew off. They were going so fast, like they expected that they would lose their energy by the time they got up, and they would just kind of go over the hump and then right off. Yeah. Because it's like 2 drops, right? Has anyone ever done the one at West End where you stand on the thing and they just open the door and you fall? No, it's really cool. You should try it sometime. Okay, and it's like a kind of a coil, and I think you do a vertical loop as well. Okay, so yeah, you stand on this door, and then the door just opens up, and you fall into the thing, and okay, down you go and do a vertical loop. Same idea, but it's pretty freaky. They also have the one that's just a big thing
Yeah,
where
they
you can
have
go
like
really
a
fast.
yellow one that's like that, and then
Yeah.
the purple one has 2 loops. I
That's
think I
two
saw
loops.
someone get stuck up there at one point.
Yeah.
I had to stop it.
It's gotta be embarrassing. You gotta like pull the section up and get you out. Yeah. Okay. Everybody with me on how that works? All right. Okay. I want you to write this one down. Let's see what you remember from Science 10. See if we can solve this one. I'll give you a few minutes. Okay. Assuming this is an isolated system, no friction or anything like that. Okay. Motorcycle rider rides off of this cliff. Straight off. Okay. It's 70 meters above the river in the middle of the canyon. So it's like the Grand Canyon. Okay. Like that. Did we watched the jumping over the Grand Canyon, right? Okay. Did we? Oh, we'll watch it again if we didn't. Okay, so we ride off of this, okay, and we land on the other side. All right, on the other side, okay, where we land has a height of 35 meters. I want you to calculate how fast the motorcycle is going when it hits the ground on the other side. Did I give you the mass of the rider? I did not. I'll tell you that the mass of the bike and the rider is 200 kilograms. You may or may not need that depending on how you did this last year. Okay, we have initial potential because we're 70 meters above. We have initial kinetic because we're moving at 38 meters per second. And then when we hit the ground on the other side, we still have potential because we're 35 meters above the lowest point. And we obviously have kinetic because at that point we're lower and would be moving faster. Okay, now, I usually like to do a short manipulation at this point because it saves me trouble later. What I'm looking for is VF. That would be part of that term. So can I isolate that term before I put in my formulas? Yeah, you don't have to do it this way. I just do because it's less to look at. Okay, so I'm going to subtract the potential final over to the other side. So I'll have potential initial plus kinetic initial minus potential final equals kinetic final. Okay, now I can expand it out again. Now I can put in the formulas for each one of these energy types. So m times g times h initial, my initial potential, plus 1/2 mv initial squared, my initial kinetic, minus m times g times h final, my final potential, equals 1/2 mv final squared. Okay, you may or may not do this step, and it's fine if you do, and it's fine if you don't. What is in every term? Mass. If it's in every term, that means every part is being multiplied by that number. Can I just take that number out? I can. The other reason I can take that part out is there are no non-conservative forces. That means this thing is only accelerating due to gravity. Do all things fall at 9.81 regardless of their mass? Okay, then mass doesn't matter if I'm only trying to solve for speed. If they wanted the final kinetic energy, then I would have to leave mass in because mass is part of energy. But in this case, that speed actually doesn't depend on the mass. Any mass would go that speed in this situation. All right, so if you don't like to cancel mass, that's fine. You don't have to. You can leave it in. You get exactly the same number. Chuck, you may. Okay, so now I've got to get VF by itself. So I'm going to divide both sides by 1/2. And then I'm going to square root. All right, so that's how I would get VF. Now I can plug in my numbers. So that'll be 9.81 times 70 plus 1/2 times 38 squared minus 9.81 times 35 divided by 1/2. Okay, now I find that the mistakes most people make are calculation errors on a question like this. Same with the work energy theorem problems, okay? Most of it comes from how we punch it into our calculator. So I would say you certainly don't have to do this all in one step. I rarely do. I do it like one part at a time. So I would go 9.81 times 70, enter. And then I'm gonna add to that 0.5, okay, times 38 squared. And then I'll subtract from that 9.81 times 35. Okay, and if you're really good at math, you probably realized you could just go 9.81 times 35 and skip a step, but if not, don't worry about it. Okay, now I divide that by 1/2, and I square root it. Okay, so when that motorcycle hits the ground on the far side, it will be moving at 46.2 meters per second. Okay, everybody all right with that? That's all you're ever going to be asked to do. Okay, solve for V or solve for H. Maybe on the odd question I might ask, what's the final potential energy, which is actually less work than this is. Okay, nothing you weren't asked to do in Science 10. Nothing more than you were asked to do. Okay? Exactly the same kind of questions. All right, so that's what we just did. Okay, I would like you to do number 2 and number 3. Just do number 2 for now. I've got to scroll up more for you to see number 3. Okay, so just do number 2 for now. Okay, give you a few minutes on number 2, and then we'll go through it together. Okay, so this mass is 225 meters above the ground, and it's moving at 36 meters per second. Okay, so it sounds like it's just falling, right? There's no context to the question. So our givens are, we know the mass, 55 kilograms. We know the initial height is 225 meters. We know the initial speed, 36.0 meters per second. Okay, calculate the velocity when it reaches a height of 115. So there's our final height, 115 meters, looking for VF. So same manipulation as the motorcycle question we did just a minute ago. All right, it says use the law of conservation of energy, so that means that I can assume that this is an isolated system and there's no friction or anything like that. So EI and EF are equal. Okay, I have initial potential and initial kinetic. I also have final potential and final kinetic. What I'm looking for is part of the final kinetic, so I'm going to move the final potential over right now. So initial potential plus initial kinetic minus final potential equals final kinetic. Okay, now I can expand again. mgh initial plus 1/2 mv initial squared minus mgh final equals 1/2 mv final squared. I'm going to cancel mass. It's in every term. Okay, and I'm going to divide both sides by 1/2. Okay, and square root. And plug in my numbers. 9.81 times times 225 plus 1/2 times 36 squared minus 9.81 times 115 divided by 1/2. Okay, so I did it piece by piece the last time. I'll show you what it looks like if you do this all in one step. So you need a lot of brackets. Okay, so 9.81 times 225 plus 0.5 times 36 squared. Nope, yeah, times 36 squared minus 9.81 times 115. Close the brackets. A divided by brackets 0.5 brackets. I think maybe the third bracket. Okay, yeah. All right, so that means our final speed there is going to be 59. No, we have 3 sig digs. 58.8 meters per second. All right, so if you do it that way, like I put in 1 extra set of brackets, I only needed 2. Okay, but you do have to use a lot of brackets if you want to try and do it all in one step. I find it's way easier to make a mistake that way than it is to do it one piece at a time. Okay. Plus, the benefit of doing it one piece at a time is you can scroll up and grab the last correct number and go with it from there. Just a thought. Okay, now, this would be what I would consider the mother of all questions. Okay, like, I wouldn't put this on a final exam, even though that would be the most appropriate place for it. And it's because it's, well, if it was on a final exam, it would be brutal. It involves you having to use some stuff you haven't used since the kinematics unit. So a little bit of X and Y components and even a little bit of projectile motion. And the law of conservation of mechanical energy. Right? That said, I think you can do it. And I want you to think about it, because it's a good exercise sometimes to do a question that's really challenging. So here's the setup I'm going to give you, just some things to keep in mind when you do this. The mechanical energy at every point is the same. Okay? So the moment it's fired, okay, here in the net, okay, it's the same mechanical energy everywhere. Now, some things to think about from Unit 1. This is a projectile. Okay? When he's here at the highest point, is he still moving? But only horizontally. You might be able to calculate using some projectile motion stuff how fast he's going there. Or you might be able to calculate his height above the launch point, which also might be useful, using some projectile motion stuff from the last unit. Okay? Using that and law of conservation of energy, which you learned in grade 10, you can solve this question. Does it take a little thinking? Sure it does. But you can do it. And I'll even let you work together. Okay? Give you a few minutes on that. Okay, let me ask you this. Is energy a scalar quantity or a vector quantity? It's scalar. Okay, so at the beginning, they tell me that he's moving at 21 meters per second at an angle of 20 degrees above the horizontal. Okay, in terms of energy, does this part matter at all? His energy is based on how fast he's going, not which way he's going. I could have shot him straight downwards or straight upwards. It wouldn't have been good for him, okay? But it would have been the same in terms of his kinetic energy. He has kinetic energy because he's moving at 21 meters per second. So at the moment of launch, VI is 21 meters per second, and HI is 15 meters. And I know his mass, 56 kilograms. Can I calculate his mechanical energy right now? Is that his mechanical energy at every point in the flight? It is. So that's a useful thing to have right off the bat. Agreed? Okay, so let's calculate that right off the bat. Okay, our mechanical energy, and we'll say it's initial because it is, even though it's also everywhere, okay, is just going to be m times g times h initial plus 1/2 mv initial squared. You'll notice I'm not canceling the masses right now because I want to find the energy, which mass is part of. Okay, so 56 times 9.81 times 15 plus 1/2 times 56 times 21 squared. Alright, so 56 times 9.81 times 15 plus 0.5 times 56 times 21 squared. Okay, so there is our total mechanical energy of the human cannonball at any point during his flight. Okay, 20,588.4 joules. Okay, so that's step one. Now I've got that. The next thing they want, okay, is the gravitational potential energy relative to the ground when he is at the highest point of his flight. Do I know how high he is at his maximum height? I don't. And I could go through a whole bunch of projectile motion stuff to figure out what it would be, or I could use way less projectile motion stuff and figure out how fast he's going here. Because at that point, he's only moving horizontally. And I can calculate how fast he's moving horizontally by finding the x component of his launched velocity. Okay, so here's what I mean by that. Back in Unit 1, when we did a projectile motion problem, okay, this was 21 meters per second, and this was 20 degrees. Okay, this was v horizontal, and it's constant. He travels at that horizontal velocity the entire time until he hits the net. So that's how fast he's going right here. If I can figure out how fast he's going right here, can I calculate his kinetic energy right here? Once I have that, can I just subtract that from that number and get his potential? I can. Okay? And it's way less work than figuring out what his maximum height would be. Because to do that, I've got to calculate this side, and then I've got to do an acceleration calculation, and then this is one calculation. Okay, so I'm just going to calculate what v horizontal is right now. Cos of 20 times 21. Okay, so horizontally he's moving at 19.7 meters per second. So I'm going to say right here, okay, that's his VF, 19.7. Okay, I'm going to calculate his kinetic energy. 1/2 times 56 times 19.7 squared. Okay, there's his kinetic energy at his highest point. Now I just take his total mechanical energy and subtract the kinetic energy. Okay, there's his potential energy at the highest point. Okay, everybody with me there? All right, that's the hardest part of that question. Part B is way easier. Okay? But part A, even though it really didn't involve that much math, what did I have to do? I had to do one trig calculation, a kinetic energy calculation, and I had to subtract. Okay? I mean, by themselves, in isolation, none of those are hard calculations. The tricky part was putting all those ideas that come from different units together to get there. That's the hard part. Okay? That's physics. The math is never all that hard. Okay? Everyone kind of follow me there? Okay? Like I said, I knew you guys could figure that out. You had all of the skills in place. It's just been a really long time since we did any kinematic stuff. Okay. All right, for part B, it's just like the other ones that we've been doing, right? It's just a basic conservation of energy question. I already know what the total mechanical energy is, so I'm just gonna say that 20,588.4 joules equals, okay, our final potential plus our final kinetic. Okay, that's the same as saying EKI plus EPI, but I already know the numbers, so I'm just gonna make my life a little easier. Okay, I'm trying to find how fast they're going, so I'm gonna bring the and final potential over, so I'll have 20,588.4 joules minus M times G times H final, okay, equals the final kinetic. That's all they want how fast. Okay, equals 1/2 mv final squared. All right, I can't cancel m here. Why not?
It's not in everyone.
It's not in every one. Okay, it's part of this number, but it's not. I can't treat it the same way. Okay, so I got to leave the m's in. That's fine. I'm just going to divide by half of m and square root. That'll leave me with VF. Okay, so 20,588.4 minus 56 times 9.81 times 2 divided by 1/2 times 56, and that should get me my final speed. All right, so 20,588, okay, minus 56 times 9.81 times 2, okay, divided by 0.5 times 56, square rooted. 26.4 meters per second. Okay, everybody with me there? I would not give you a question like part A on a unit exam. Okay? But it's worth doing, right? It expands our minds a little bit. Makes us see connections we wouldn't see. Let's just do an easy ones. Okay, we'll leave it there, guys. I haven't had too many people come in to ask questions, but we got a unit exam on Monday. Okay? Make sure you're preparing for that. The only thing that's on that unit exam, there's like one multiple choice question, okay, on it that we haven't covered is power. And that's what I'm going to do after we do the quiz tomorrow. And then that's it. We've covered everything in this unit. All right, so you can definitely start studying. I did post some stuff in Google Classroom yesterday, but there is a review package at the end of the unit workbook, the Unit 2 workbook. The review package is basically the last page, but I also posted it. And then we'll do a unit exam review on Thursday. Okay? Friday we'll kind of just tidy everything up from the unit. Okay? All right.